Precipitation reactions are an important class of chemical reactions that take place in aqueous solutions. In this video, we'll look at precipitation reactions in more detail, work out how to predict the products of chemical reactions involving precipitation processes, and actually see whether a chemical reaction will take place at all. So precipitation reactions are an example of a double displacement or metathesis reaction. And let's just remind ourselves what they are. We've got a general reaction scheme here, AB plus CD going to AD plus CB. What's happening here is A is displacing C to form the compound AD, and B at the same time is displacing D to form the compound CB. In effect, what we've got is a swapping of parts. We've got substance A coming together with substance D and substance C coming together with substance B. So the example that's shown in the picture here and shown in other videos in this series is a mixture of a lead nitrate solution with a potassium iodide solution. And in effect what happens here is the lead displaces the potassium from the potassium iodide to form lead 2 iodide, which is the yellow precipitate that is formed, and at the same time the nitrate ion is displacing the iodide ion from the potassium iodide to form the potassium nitrate aqueous solution. So what we've got here is lead 2 plus ions coming together with iodide ions, and when the lead 2 plus ions are in the presence of nitrate ions, they're quite soluble. All nitrate salts are soluble. And when iodide ions are in the presence of potassium ions, they are also quite soluble and they readily form aqueous solutions. All group 1 metal salts, including potassium salts, are soluble and form aqueous solutions. However, when lead ions, lead 2 plus ions, and iodide ions come together, they're insoluble in the presence of each other. Despite being soluble in the presence of other ions, when they're in the presence of each other, they're insoluble. And what we get is that insoluble yellow precipitate being formed. And we can predict that from our solubility rules. We know that most iodide salts are soluble, with the exception being the big three of silver, lead, and mercury, and this is one of those exceptions. This equation up here is the net ionic equation for that precipitation reaction, and there's the full molecular equation written out, and we'll deal with both of those in just a moment in more detail. So in order to predict the products of a precipitation reaction, we're going to go through a series of steps, and the first one is to write the formulas of the reactant solutions in the form of a molecular equation. So any precipitation reaction has two solutions being mixed together, and the idea here is to predict A, whether a precipitate is going to form at all, and then if so, what's the identity of that precipitate, and then we need to balance the equation and do a few other things. So here I've written the chemical formulas of the reactants down in the form of a molecular equation. We've got a silver nitrate solution and a barium chloride solution. The next step is we assume that the reactions actually react, and we write down the products based on a double displacement metathesis reaction. That is, we swap the anion and cation pairs around. And so the silver is now going to hook up with the chloride. The silver is the positive cation of silver nitrate, and it's going to hook up with the negative anion of the barium chloride. And at the same time, the barium and the nitrate are going to get together. So what we've done there is just swap the anion and cation pairs. The next thing we have to do is make sure the chemical formulas for these two potential products are actually correct. So if we look at silver chloride to start with, silver is a 1 plus ion, chloride is a 1 minus ion. When they come together to form an ionic compound, the 1 plus and the 1 minus cancel each other out, and they will come together in a 1-to-1 ratio. So silver chloride, AgCl, is the correct chemical formula there. What about barium nitrate though? Barium is a group 2 metal, it forms a 2 plus ion. The nitrate ion is a 1 minus ion. These will not come together in a 1-to-1 ratio. If we do our crisscross method here, we can take the 2 from the 2 plus charge of barium and bring it down as the subscript for nitrate. We can take the 1 from the 1 minus charge of nitrate and bring it down as the subscript for barium. And so what we end up is barium nitrate, BaNO3 2. So we need to make sure we write that chemical equation, that chemical formula out correctly first before we go on and try and do anything else. Step 3, we now need to balance the equation. Now we've gone to some trouble to make sure we've got the chemical formulas of each of these substances right in this chemical equation. So now we don't mess around with any of the subscripts. The only thing that we can do to balance this chemical equation is to put the stoichiometric coefficients out the front. So make sure you only change the stoichiometric coefficients. The other thing about balancing equations involving polyatomic ions is to keep the polyatomic ions intact and don't try and balance the individual atoms separately. So here we can see I've got 1 nitrate ion on the left hand side and I've got 2 nitrate ions on the right hand side. The idea here would be to just balance the nitrate ions as a whole. The other things that are not in balance at the moment, I've got 2 chlorides on the left hand side and I've only got 1 on the right hand side. And so to balance this equation here, if I put a big 2 out the front of the silver nitrate on the left hand side and a big 2 in front of the silver chloride, you can see here now that I've got 2 silvers on each side, I've got 2 nitrates on each side, I've got 1 barium on each side, and I've got 2 chlorides on each side. So this equation is now balanced. Step 4 is we're going to use our solubility rules to determine if any products will form insoluble salts. So we need to assign either an AQ or a solid subscript there. If it's an insoluble salt, it will form a solid precipitate and we give it the S subscript. If it's a soluble salt, it will form an aqueous solution and we give it the AQ subscript. So we go to our solubility table here and we see that most chlorides are soluble in water, but there is an exception here that's relevant for us. Silver chloride is an exception. And so silver chloride is insoluble in water and we are going to put the S subscript there to indicate that we've got the solid precipitate forming. And that's the insoluble silver chloride precipitate you see forming in the photograph there. In terms of the barium nitrate, we see that all nitrate salts are soluble and there are no exceptions there. So we're going to put the AQ subscript next to the barium nitrate. All nitrate salts form aqueous solutions. The last step, and you may not have to do this depending on the context and the situation, is to write out the net ionic equation. What's the net chemical change that's actually taking place here? And to do that, we have to write out the full ionic equation and we have to identify spectator ions and then we cancel them out. So let's have a crack at doing that. There's the full molecular equation that we've just balanced. We've got our stoichiometric coefficients there and we've got all our subscripts appropriately written. The full ionic equation has all of the strong electrolytes in the full molecular equation written out with their ions separated out as individual ions. So the 2 silver nitrate, we got 2 silver ions and 2 nitrate ions. The strong electrolyte barium chloride separates out into a barium 2 plus ion and 2 Cl minus ions. The silver chloride solid is not a strong electrolyte, it's not soluble in water, and so we're still going to keep it written as 2AgCl solid. And then the strong electrolyte barium nitrate is written as separate barium 2 plus ions and the 2 nitrate ions there. Now we can see that these 2 nitrate ions here undergo no physical or chemical change from the left hand side of the equation to the right hand side. So these 2 nitrate ions on each side of the equation are spectator ions. They don't take part in the reaction and we can effectively cancel them out. The other spectator ions that undergo no physical or chemical change are the barium ion on the left-hand side there and the barium ion on the right-hand side there. So that just leaves over the 2 silver pluses plus the 2 Cl minuses to give us 2 AgCl solid. And there's our net ionic equation. Now you'll notice that there's a 2 in front of every substance in this equation. We can effectively cancel that out, get our chemical equation down to the lowest whole number ratio of all substances involved, and we have our net ionic equation of 1 silver ion plus 1 chloride ion going to AgCl solid. So just a summary, the steps in predicting the products of precipitation reactions: write the formulas of the reactant solutions in the form of a molecular equation. Assume that the reactants actually react and write down the products based on a metathesis double displacement reaction where we just have a swapping of the anion and cation pairs. We then balance the equation, make sure we write down the correct chemical formulas first, and then make sure we use our solubility rules to determine the subscripts for those products. Will any insoluble salts form? If so, we are going to get a precipitation reaction occurring. And then finally, if you need to write out the net chemical change that's actually happening, then write out the full ionic equation, cancel out the spectator ions, and you can get to the net ionic equation.